I've created a cluster of things right here, and then I copy and pasted another cluster, and I have a couple of these off canvas. And what I want to do is represent the number of things we have in each of these clusters in different bases and in different number systems. So first, we're going to do it in base 10, sometimes called a decimal number system. Decimal, you know the prefix deci, it refers to 10, decimal number system. When people talk about a decimal number system, they're not just talking about what we traditionally associate with decimal numbers to the right of the decimal point. They're talking about base 10, so in a decimal number system. So the way you would think about it is the way you would think about, really, well, I mean, one way to think about it is how you think about money. If you have a bunch of money, or you're trying to represent a bunch of money with the smallest possible bills, you'll see the biggest, you'll try to figure out the biggest bill that is smaller than that amount of money, and you would start there if you wanted to have the fewest number of bills. So over here, if we're in base 10, we want to find the biggest power of 10 that fits into however many objects we have here. And let's just count it real quick. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34. I might have missed a few, but the bottom line is 100 does not go into this, but 10 would. So we can divide the biggest power of 10, or the biggest power of 10, I should say, that is divisible into this is 10. So let's divide this into as many groups of 10 as we can. So let's see, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So let me separate these off. So that is 110 right over there. Let me make sure I counted that right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let me find another group of 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this right here is another group of 10. And then I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this right here is another group of 10. And then this over here is not a group of 10. This is just 1, 2, 3, 4, 5. So it looks like there's 35 objects here. So I can represent these three groups of 10. So let me actually just write down in words first. So we have 3 tens. So we have 3 tens, or we could consider it 3 groups of 10s. And then in what's left over, I can't divide 10 into it, so I have to go down to a lower power of 10, and that's 1. So how many 1s are there right over here? So then we have 1 1, 2 1s, 3 1s, 4 1s, 5 1s. So it's 3 10s plus 5 1s. And the way we would represent it in a base 10 number system, we have a tens place. So in the tens place, so let me write, in the tens place, we would write 3. And then in the ones place, we would write 5. And so we would just associate this is 35. But this is just representing it in a decimal number system. We've gotten used to this, but this is just one of really an infinite number of number systems. Now let's do the same thing with the same cluster, but let's do it in base 2. Let's do it in base 2, or where we can only represent it with 2 different digits. In base 10, you have 10 different digits to play with. Or you could call this a binary number system. Binary number system. You only have 2 digits. Binary number system. So what is the largest power of 2 that can fit in this? Remember, we want kind of have the fewest number of coins or bills. So we want to put the largest power of 2 that would fit into this. So what would be the largest power of 2? So we have 35 things. So let's see, the largest, 2 to the 4th power is 16. 2 to the 5th power is 32. So 32 goes into this. So let's find ourselves a group of 32. Well, really, we could just exclude 3 things. So this right over here is a group of 32. So we have 1, 32s. Let me just write it like that. And then we have no 16s, no groups of 16s here. And then we have no, because 16 can't go into what's left over. We have no groups of 8. We have no groups of 4. But then we have groups of 1. Remember, 1 is just the low. It's 2 to the 0th power. So we have 1, 2. Oh, let me be very careful. I skipped 1. So let's draw our places here. So we looked at groups of 32. 32 did go into it. Then you go to 16. Then you go to 4. 4 still can't go into this remainder right here, but 2 can. So now let's do a group of 2. So a group of 2 would look just like that. So we have 1 twos, 1 twos. And then what we have left over is just one group of 1s. So then we have, let me just in a new color, one group of, that's not a new color, one group of 1s. No, that's still not the same. Having trouble switching color. One group of 1s. So 1, 1s. So how would we represent this in base 2? And to do that, let's just think about our places. This is the 1's place. That's the 1's place. This is the 2's place. That's the 2's. That is the 4's place. I'm running out of space here. So this right here is the 4's place. This right here is the 8's place. Let me do this a little smaller so I don't bump into our diagram. So that is 8's. 8's. Now this right here is 16's. 16's. And then we're just going up. We're multiplying by 2 in each place as we go to the left. And then this right here is the 32nd's place. 30. And I'm writing it out so we don't confuse. I could write the base 10 symbols here, but then that could be kind of confusing. So let me just write the words here to say that, look, these are the places, and I don't want to use base 10 to represent base 2 places. So we know from kind of grouping this, the largest group, we have 132's, so we write a 1 in the 32's place. There's no groups of 16 here in the leftover, so there's no groups of 16's. There's no groups of 8's here. There's no groups of 4 here. There is a group of 2's. So there's one group of 2's. And then there's one group of 1's. One group of 1's. So 1, 0, 0, 0, 1, 1 is how you would represent this number, or this number of things, or 35 things, in base 2. In base 2. Now what I want to do is take it to the next level. Base 2 has fewer digits than what we're used to in the decimal number system. What happens if we had more digits? So let's go to base 16. And this is fascinating. Base 16. Base 16. Or a hexadecimal. Hexadecimal number system. Hexadecimal number system. No, I don't have to write number system. Hexadecimal. And here we're going to have 16 digits. So we're going to have all of the traditional digits. Let me write them all out. We're going to have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And so this is 10 digits right here. But now we're going to extend the number of digits we can deal with. So instead of having to reuse these digits to represent 10, we're going to represent 10 with an A. And we're going to represent 11 with a B, and represent 12 with a C, and represent 13 with a D, represent 14 with an E, and then represent 15 with an F. So now we have 16 digits. We have 1 through 15 plus 0. Remember, in base 10, you have 1 through 9 plus 0. So you kind of have symbols that go all the way up to whatever your base is. So in this situation, don't be confused. This A, when we're talking in hexadecimal, represents 10 objects. This B would be, if I say, hey, you owe me B dollars, I'm telling you that you owe me $11. It's just another way to represent 11 instead of you doing a 1 and a 1 that we would do in base 10. So if you had these digits, how would you represent this many things? So remember, we're in base 16 now. So let's draw the number of spaces. So you're always going to have your 1 space. If you know your powers, that's 16 to the 0th power. And then if you multiply that times 16, you have your 16's place. You have your 16's place. Because we're in base 16, or hexadecimal. And then if you go one place more, you have your 256th place. And I'll write it down, but I'll write it in quotes. Your 256th place. And I got 256 because that's 16 times 16, or 16 to the 2nd power. So how would you represent this? So first of all, does 200, and we could keep going up by multiplying by 16. But does 256 go into this thing right over here? It doesn't. We know we only have 35 things right here. So we won't use the 256 place when we represent this number. And so 16 does go into this. So how many groups of 16 do we have here? So let's count it out. Let me do it with a new color. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So hopefully I didn't lose any. So that's one group of 16. Let me count it again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So that's one group of 16. Let's get another group. See if we can get another group of 16 in here. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So all of these right over here are another group of 16. It's another group of 16. And then we definitely can't divide 16 into what's left. So we have two 16s. We have two 16s. And then the only other place we have is ones. And then we have three ones. 1, 2, 3. And we have three ones. So in base 16 in hexadecimal, we have two things in the 16s place. So we would put a 2 over here. Let me do that same color. We would put let me do that same blue. So we have two 16s and we have three ones. Three ones. And you might be tempted to say, oh, that's just 23. No, we're in base 16 here. And usually, sometimes people will tell you what base you're in. But we're in base 16. We're in base 16. So this isn't just 23. This is representing 35 things. It's telling us we have two 16s and three ones. And it all adds up. 2 times 16 is 32, plus three ones is 35. I'll do more examples of this in the next few videos.